Hi, this is Roland from Brain MRI. This is a very special video because together with this video we will release the frequently traveling human phantom dataset. Let me explain what this dataset is about. During the last years, a colleague visited a great number of radiology centers, and during each visit the brain of that person was scanned with an MRI using a 3D T1 weighted gradient echo sequence. The good thing is that the data can be downloaded for free. The link can be found under this video. The data provides data from 557 images of the brain of a single healthy male volunteer. Scans were acquired on 116 different MRI machines, and for some scanners the volunteer was scanned in several imaging sessions with different MRI protocol settings. Altogether, the dataset includes data from 157 imaging sessions with 3 to 5 repeated scans in each session. As mentioned, the data were acquired on 116 different physical MRI machines and 24 different scanner models were used for the acquisition. Here you see the frequency of the 24 different scanner models. As you can see, the majority were scanned by Siemens, followed by Philips and then GE scanners. To give you an impression of the data, we now quickly go through some example images. We show you some example images of the 19 Siemens era scanners which are contained in the dataset. This is the first example of the Siemens era scanner. For each image we showed 3 orthogonal views. In addition, a histogram over the image gray values is shown. This is the first example. Let's have a look at some other examples. Now, as you can see, although these examples were acquired with the same scanner model using a similar acquisition protocol, the contrast between gray and white matter as well as the image quality can be quite different from scanner to scanner. So now we use the dataset to estimate the inter-scanner variability of a well-known brain segmentation software package, the SBM12 software. We use this software and segment all images in our dataset into the gray matter, the white matter and the fluid component of the brain. And from the segmentations we calculate the brain parenchyma volume, so the brain volume, BPV, which is the sum of the gray and the white matter, as well as the total intracranial volume, which is the sum of the gray matter plus the white matter plus the fluid component of the brain. The question is, how much does the brain volume depend on the scanner? Since it is the same brain, the brain volume should be approximately the same for all scans, right? As you will see, this is not the case. To make it a bit more interesting, we will relate the interscanner variability to the intersubject variability. Interscanner variability describes how much the brain volume depends on the scanner hardware, whereas the intersubject variability provides information to which extent the brain volume differs from individual to individual. Therefore, we analyze a second dataset, which comprises MRI images of nearly 5,000 healthy individuals. And that data was acquired on 160 different scanners. Since the data contains data from different scanners and from different individuals, we can expect that the data reflect the interscanner variability as well as the intersubject variability. To estimate the intersubject and the interscanner variability, we first should remove the influence of the nuisance variables age and head size. For this, the brain volume is modeled with a bivariate quadratic function with age and TAV as variables. And then we compute the least square fit through the data and we obtain a surface which is shown here. A point on that surface tells us the expected average brain volume for a specific TAV and age. To remove now the influence of the TAV and age, we compute the distance of each point to that surface. And we obtain a univariate distribution which reflect the intersubject and the interscanner variability. Let's now plot the FTHP data within the normal database. These are the brownish points you see here. We also compute the distances to the same surface and we get a second distribution. This distribution reflects the interscanner variability. And as you see, the interscanner variability is quite large and covers a significant proportion of the distribution of the normal database. In summary, the frequently traveling human phantom datasets provides a unique possibility to study intra- and interscanner variability of brain quantification tools. The data can be downloaded for free. We formally introduced the FTHP dataset in this publication. So if you want to know details, please follow the link under this video. If you find the content of this video useful, please press the like button. This will help others with similar interest to find this video. Thank you for watching this video.